This video is titled Orbital Speed and Escape Speed. Question 1. The following problem refers to escape speed. Part A. Define escape speed. This is also called escape velocity. It's the minimum initial speed required for a projectile to escape a planet's gravitational pull and go to infinity. Part B. What are some assumptions made when defining escape speed? Well, there's no force of air friction, no effects of gravitational fields from other objects in space. Part C. For which objects does escape speed apply to? Projectiles. Part D. For which objects does escape speed not apply to? It's any object with an engine, like a rocket. Part E. Use the law of conservation of energy E initial equals E final to solve for the equation of the escape speed of an object leaving the gravitational pull of a planet. What is the minimum speed needed for an object to escape the gravitational pull of the Earth? So let's use the law of conservation of energy. E initial equals E final. So E initial, we're at the surface of a planet, and E final is the energy we're at infinity. So in the beginning, at the surface of a planet, we're going to have the kinetic energy of that object at the surface of a planet going straight up, plus the gravitational potential energy of that object at the surface of a planet. It's going to equal the kinetic energy at infinity plus the gravitational potential energy at infinity. Well, if we want to find the escape speed, we need the minimum speed possible to escape the gravitational pull of the surface of a planet. So we're going to let V equals 0 when we are at infinity. And we are going to let little r equal infinity for the gravitational potential energy at infinity. So on the left side, we get 1/2 mv squared plus minus gmm over r equals 0 plus 0. Let's solve for V projectile. This is the minimum speed required for an object to escape the planet's gravitational pull. For Earth, we're going to plug in the values for the mass of the Earth, the radius of the Earth, and the gravitational constant. We get about 11,000 meters per second. So we need to throw an object up at about 11,000 meters per second for it to escape the gravitational pull of the Earth. Now this is without any engines and rockets. It's like a ball. Question 3. You might want to derive this equation with your teacher. A planet is orbiting in a circular motion with a constant speed around a star like the Sun. Part A. Use Newton's law of gravitation and the equation for centripetal acceleration to solve for the speed squared of a planet moving around a star. Place a box around your answer. In both equations, r is the distance for the planet to the star. So F equals ma, and a is equal to v squared over r. So just solve for v squared. You get this. Now take your solution from part A and multiply both sides by mass of the planet over 2. This new equation is equal to the kinetic energy of the planet. So kinetic energy is 1/2 mv squared. Place a box around your answer. So multiply the left side and the right side by m planet over 2. You get 1/2 mv squared on the left side. You get gmm over 2r on the right side. So gmm over 2r is the kinetic energy of a planet moving around a star. Part C. Substitute your answer from part B to the total energy of the orbiting planet, which is this. Kinetic energy plus gravitational potential energy. Place a box around your answer. Your answer should have only one fraction. So we're going to put this yellow equation from part B, and we're going to put it here. We're going to substitute it here. And we're going to substitute it here. And here. and finally here. So now we get minus gmm over 2r. That is the total energy of a planet going around a star. Memorize this derivation. Part D, is the total energy positive, negative, or zero? Why? The total energy is negative if the planet is in circular motion or orbital motion around a star. The planet is not free. So the total energy will be positive if it has enough kinetic energy to move to infinity. If the total energy of the object is positive, then the object will be free. So this object is not free. And since it's not free, the total energy is negative. Part E, draw an energy versus distance graph. On this graph, draw the kinetic energy versus distance, potential energy versus distance, and total energy versus distance graphs. So these are graphs of an object going around a star in circular motion. So kinetic energy is 1/2 mv squared, that's always positive. Potential energy is minus gmm over r, which is always negative. Sorry, minus gmm over 2r. And the total energy is minus gmm over r. I apologize. Potential energy is minus gmm over r, and total energy is minus gmm over 2r. And as the distance increases, like r, 2r, 3r, 4r, 5r from a planet, the farther away you go from the planet, the total energy gets closer to zero because it looks like you're going in a straight line. The kinetic energy goes closer to zero and the potential energy gets closer to zero. Do memorize this graph. Question 3. An object is orbiting a planet. It encounters a small viscous drag force due to the atmosphere. Describe the subsequent motion of the object. So the total energy of the object decreases, its distance from the center of the planet decreases, and its speed increases. So then the object is going to eventually hit the Earth, or the surface of the planet. Question 4. A rocket with a mass of 6.4 times 10 to the 4 kilograms is orbiting Jupiter's moon Callisto. Callisto has a radius of 2.4 times 10 to the 6 meters and a mass of 7.35 times 10 to the 22 kilograms. Part A. What would the velocity of the rocket have to be in order for it to orbit Callisto at an altitude of 4.6 times 10 to the 3 kilometers? So, we have this equation, which we derived earlier. And we could also derive it from here. F equals ma equals mv squared over r, solve for v. R is the distance of the rocket from the center of the planet, or the center of the moon Callisto. So that's why we have these two fractions in the denominator. The radius of Callisto and the distance above Callisto, the surface. Part B, what would be the gravitational force between this rocket and Callisto while orbiting at this altitude? So they want the gravitational force, just use this equation. Part C, what would be the kinetic energy of this rocket while orbiting Callisto at this altitude? So just use 1/2 mv squared. We solve for V from part A. Part D, what would be the gravitational potential energy of this rocket while orbiting Callisto at this altitude? Just use this equation. Plug in what we know. Part E, what would be the total energy of this rocket while orbiting Callisto at an altitude of 4.6 times 10 to the 3 kilometers? So we're just going to add up parts C and D. Part F, what would be the total energy of this rocket while sitting at rest on the surface of Callisto? Well, it's sitting at rest, so kinetic energy is 0. 1/2 mv squared is 0. And you can see the total energy is negative. Don't freak out. Part G, how much kinetic energy would you have to give to this rocket while sitting on the surface of Callisto in order to put the rocket into orbit around Callisto at an altitude of 4.6 times 10 to the 3 kilometers? So this is the law of conservation of energy here. The total energy at the surface is equal to the total energy at 4,600 kilometers above the surface of Callisto. So just solve for kinetic energy at the surface. And you've already solved for these three values from parts C, D, and F. Part H, with what velocity would this rocket have to be launched from the surface of Callisto in order to go into orbit around Callisto? So just take your solution from part G and solve for V. Part I, with what velocity would this rocket have to be launched from the surface of Callisto in order for the rocket to escape the gravitational effects of Callisto? So use the law of conservation of energy. So you need to throw an object up with the minimum speed of this for it to leave Callisto's gravitational pull. Question 5. A rocket which has a mass of this is initially sitting at rest on the surface of the planet Venus. Venus has a radius of this and a mass of this. Part A. What is the total energy content of this rocket while sitting at rest on the surface of Venus? So it's sitting at rest, so kinetic energy is 0. Gravitational potential energy is minus gmm over r. Don't freak out because the solution is negative. Part B. What velocity will be required for this rocket to orbit Venus at an altitude of 550 kilometers? So F equals ma equals mv squared over r. Solve for v. Part C. What total energy is required if this rocket is to orbit Venus at an altitude of 550 kilometers? So we took our solution from part B, which is kinetic energy, and we just add it to gravitational potential energy. Part B gave us the velocity, so we could just plug that into 1/2 mv squared. Part D, with what velocity should this rocket be launched from the surface of Venus in order to go into orbit around Venus at an altitude of 550 kilometers? So use the law of conservation of energy. The total energy of the rocket at the surface is equal to the total energy of the rocket at 550 kilometers above the surface. Part E, with what minimum velocity should this rocket be launched from the surface of Venus in order to escape the gravitational effects of Venus? So once again, use the law of conservation of energy. The total energy at the surface of Venus is equal to the total energy at infinity. It says minimum velocity, so just let's assume that the velocity at infinity is 0. That's why 1/2 mv squared is 0, because v is 0. And to escape the gravitational effects of Venus, r is going to be infinity at the end. So minus gmm over r, if r is infinity, minus gmm over r is going to 0. Part F, what would be the velocity of this rocket when it is very far from Venus? if the rocket is launched from the surface of Venus with a velocity of this. So use the law of conservation of energy and solve for velocity. It says very far from Venus, so that's why gravitational potential energy at infinity is equal to 0. Question 6. A rocket which has a mass of this is sitting on the surface of Neptune. Neptune has a mass of approximately this and a radius of approximately this. The rocket is to be launched from Neptune's surface with the intention of going into orbit around the planet Neptune at an altitude of this. With what minimum velocity should this rocket be launched from Neptune's surface in order to go into orbit around Neptune at the given altitude? So use the law of conservation of energy. The total energy of the object at the surface of Neptune is equal to the total orbital energy when we're above Neptune. So this is equal to the minimum velocity, and just solve for R. Solve for V. Part B. What will be the total energy content of this rocket while orbiting Neptune at the given altitude? So it says total energy, so let's just use this equation. Part C. How much kinetic energy must be added to this orbiting rocket if it is to escape the gravitational effects of Neptune? It's this much. Part D. What velocity must this orbiting rocket attain in order for it to escape the gravitational effects of Neptune? So just set this equal to 1/2 mv squared and solve for V. Part E. Suppose that somehow the planet of Neptune were to change into a black hole. What would be the maximum radius of Neptune have to be in order for it to become a black hole? So this is called the Schwarzschild radius equation. 2gm over c squared. Question 7. A rocket is orbiting the planet Jupiter at an altitude of this. Jupiter has a mass of this and a radius of this. What is the velocity of this rocket while orbiting Jupiter at this altitude? So F equals ma equals mv squared over r equals gmm over r squared. Solve for V. Part B. What is the total energy content of this rocket while orbiting at this altitude? So we know it's kinetic energy plus gravitational potential energy. Part C. How much additional energy must this rocket acquire in order to leave orbit and escape the gravity of Jupiter? So just take the magnitude of part B. Part D. Suppose that this orbiting rocket is given an additional energy. What will be the resulting velocity of this rocket when it's very far from Jupiter? And that's how you do it. Part E. What will be the maximum radius of Jupiter have to be if it was to become a black hole? So we use this Schwarzschild radius equation again. Question 8. A rocket which has a mass of this is moving through space with a velocity of this when it begins its approach to Saturn. This rocket would like to go into orbit around Saturn at an altitude of this. Saturn has a mass of approximately this and a radius of approximately this. Part A. What is the initial total energy of this rocket before it approaches Saturn? 1/2 mv squared. What total energy is required in order for the rocket to go into orbit around Saturn at the given altitude? It's this.